Today I will try to explain VAE part of the world model. So we will use example of MNIST dataset, handwritten dataset, digit dataset to generate handwritten image. So VAE is actually a kind of autoencoder. So it's a special kind of autoencoder. So it's also called generative autoencoder, generative model. That means this model can generate data. So, standard autoencoder, it can generate data that is already in the input image. So it's kind of a variation. That means this variation autoencoder tries to learn the distribution of input data, and then it will generate data, output data, which is kind of similar of the input data, but sometimes it's different. There is a variation from the data. So that means if we consider standard autoencoder, input could be of any type, like say image or text or audio, any kind of. So we are considering like say image data. We have two as an image, then it goes through a encoder, and the encoder compresses the input data and makes a short compressed representation, which is a vector h of size n.
Sadiq, maybe you want to use the next marker. Can't see anything.
Yeah, and maybe dump the one that is not working here, so that you don't pick it up again. And I have one question. How many guys do you know what autoencoder is? Are you familiar with
I just know the theory. That's what I'm looking to learn the content.
Okay, Sanjay?
Yeah.
Okay, let's
So age, which is like say size of n, then it passes through another layer, which is decoder, and decoder actually converts the hidden vector back to the original input. So again it will get output of true. So as it is a compressed representation, sometimes you may not get the exact same input as the output, but its target is to generate the same input as the output. That means basically your output yi is basically same as xi. That is the main target. So ultimately its target is to update the weights in the encoder or also in the decoder such that this criteria is fulfilled. So if you consider like say I have x as an input, and like say in the simplest example, I have one hidden layer, and it makes it creates a hidden vector of size n. Then it goes through another just one single hidden layer. Then it makes output vector of x prime. So we have two function approximator. One is for encoding part, this part, and second function approximator is for h to x bar, x prime. So this function approximator can be called phi, which is x to say x to f, and another function approximator which is say psi, which goes from f to f back to x. because we want the output to same as the input, so that's why it is same as x. Now let's say this function can be defined as h as segment function of wx plus b. Now for the second function approximator, we want x prime to another segment function sigma prime, we say w. Now x, here x is h, so it's h plus b prime. Now if we replace h by this function, it will be sigmoid of wx plus b plus b prime. So this is how we can get the output. So it works by back propagation. That means each time it will update the weight here, so that it can get the output. So now if we have a certain representation of h by using this function, you can create output data which is image or something like that. Now how can we define the loss function? The loss function can be defined as L of x prime, which could be a mean squared error. That means x minus x bar square with x minus. Then you can put the whole equation in this part, which is sigma So our main target is to
Shadek,
minimize this loss.
next time write a different W. So W, those two W is not same, right?
This W?
Oh.
Yeah. It's different. It is W prime. So for first approximator it's W. For second equation,
Yeah, it should be.
it's W prime. So the autoencoder will try to minimize this loss, and in this way it will update W and W prime, and that's how it will work. So but what is the difference between standard autoencoder and variational autoencoder? Like say in this part, autoencoder tries to gives you the actual a vector which can be directly used for the next stage. But in variational autoencoder, you will not be given the direct age. Instead, it will be given as a distribution of, like say hidden vector has a size of n. So you will get n of n mu and n variation. So it means that for each feature, it will give you the distribution of that particular feature. That means let me give you an idea.
So mean and variance.
Basically the parameter of the system.
Yeah, let's say this encoder will give you a size of a vector of mu and also a vector of variance. Like say mu will give you 0.1 and 1.2, and variance will give you, like say system deviation, it's 0.2 and 0.5. So from these two vector, this part for the next stage, it will sample from these two distribution, and it will get the provide input for the decoder part. So it's not giving you the actual H vector. Instead, it will try to learn the representation of the input. What is the distribution of each individual feature, and then this encoder will generate this mu and variation vector. Then from the sampling, it will provide the input for next stage and will build the input image as I said.
Why we have to? What's the benefit of the sampling?
The benefit of sampling is that even for the benefit of sampling is that, like say, if we have a particular H hidden vector,
Mm-hmm.
it will give you just exact same output which was in the input.
Mm-hmm.
That means if you don't have that particular image,
Mm-hmm.
this H actually useless.
Mm-hmm.
So, so if you have a like say a variation in the input, like say I have two in one way, like say I can write it in different way.
Mm-hmm.
For standard autoencoder, if I don't give this input, it doesn't know anything about this, so it cannot create a proper hidden vector for this for this particular image. So you cannot get the output. Like say it doesn't know this input, so that's why it cannot create the hidden vector. But if you in variational autoencoder, even if this input is not given, it will be able to find the distribution. Like say this has the same distribution as this input. So that then from the because of sampling, it can generate the output.
So it makes the input space continuous rather than discrete.
Rather than discrete. That means even for many different variation of the input, like say during training, I don't have all different versions of the input.
Yeah.
But as because of sampling, I try to learn the distribution of the input, which I can use later. That's the main benefit of variational autoencoder. That means standard autoencoder, it doesn't learn the distribution of the input, but in VAE it tries to learn the distribution. So that's the main difference. Like say so another thing is, like say if you put the same image like say multiple times for variational autoencoder, so for the next stage the input will be different, because it will give you the output will give you just the distribution, but before sampling, because of sampling you might get different input for the same input image. Like say it is always same, but as you are sampling, what happens? The input to the decoder part could be different.
So it could choose something else with the same distribution.
Even for same image. But as our target is, what is our target? Our target is generate the same output as the input. So what it does, it actually tries to learn the distribution. Like say, even for what can I say? So it basically learns the different way to represent the same image. Like say it tries to learn a particular distribution for a particular image. So even though I gave a different sample, as I want to match the output with the input, so even for the different sampling, my target is to predict the same input. So that's how it can learn the distribution of the input. Is it clear?
Tor, can you explain what is the benefit of generative model?
So, I'm not sure about this, but my understanding is we don't really learn the distribution of the input, but we actually learn the distribution of the features. Okay, and the reason why they use it instead of an autoencoder is that in an autoencoder, for every hidden state that you have, okay, it is possible that you have, say if you change that hidden state, right, it's possible that that latent representation is nowhere in that space that you've learned. Right?
Okay.
So that's why you sample, you basically learn the distribution of the features, and so even if the distribution that you've learned, right, since you're sampling from it, any representation of the latent state, you will be able to get an output image.
Okay.
So that's the generator models you explained.
Yeah, it is a generator.
Basically, for one input state, it is able to generate similar
Similar image.
similar images with small variations,
Right.
Yeah.
without actually having that as an input, because it's sampling the features. Now it is able, it has the capability of even recognizing images or generating images that are similar to the input but with small changes.
Okay, fair enough. Let's continue.
So, yeah. So how is a loss is defined in VAE? It's defined by two different components. One component is XH, then another then again X prime. So first component is that our X has to match with X prime. That means these two components has to have same distribution. This is one component, and another component is the distribution, the hidden states output that I'm generating. It has to have same as a standard. Like say I can generate any kind of mu and variance. It doesn't have any limit. So what do we want? We want this mu and sigma to be generated from from our approximation distribution, which will always have mu as 0 and standard deviation as 1. That means we want to generate this vector to come from a distribution of mu and 1. So our next component of the loss is defined by KL divergence. That means the distribution that we find from H and the distribution of the input should have does not the diverse mode. That means like say for one input for 2, like say I have a hidden size of 2, so I have got some input, got output, and then for another input image of 2, I want it to be close to this one. That means there should not be any gap between the object which are similar. That means for many different variation of 2, I want the hidden space to be close together into same space. That means for any there should not be so it should be continuous space. That means if there is a like say blank thing between these two, the model will not be able to tell whether it's from this for this particular class or a different class. So if the sample after sampling, if you get a output, if you get a like say vector from this space, it cannot tell whether it's from this class of 2 or from any other class. So the idea behind this KL divergence is to keep all the objects that are similar to have a continuity in their hidden space, such that when I am sampling, I can know exactly where it is coming from. If it is from here, then I can tell, oh, this is 2 that I have to generate. So, but for any other case, this space, like say for 3. So, if I sample from this space, I can tell that this is for 3.
But how are you defining? I mean, you're saying KL divergence between which two distributions?
Distribution of like say approximate distribution that I want to ultimately achieve. That means, let's say I have a standard base distribution which has a mu of 0 and variance of 1. This is the distribution that I want to achieve. So let's say this H can give any kind of mu and sigma. So what I want that this distribution has to be same as this one, such that it doesn't diverge. So
but how are you defining this one? Mu 0 and sigma?
It can be defined like say statistical model. So like say I have n random variable. All has a mu of 0 and standard deviation of 1. Like say I have n random variable which has these two components same. Like say I have a hidden size of n, so I will have a vector of n. So when I am sampling, I'll sample by keeping these two things in mind. That means I want this space to be the same as this distribution. So that's our main target.
So can you explain one more time? I'm sorry, I couldn't understand why you want make the distribution of H to be normal distribution?
I don't know exactly how they use that, but the main idea is that I want all the hidden objects to have a mean which is centered around 0. Like say, as I have defined as 0, that means all the distributions should be centered around 0, and that this variation actually tells you how far it can go.
Yeah. So why we cannot say mu is, for example, 2 and sigma is, for example, 3?
I mean, it can be used. I mean, usually they use these two parameters, but it can be used for any other distribution as a base.
Then why can they use a different mu and sigma for all dimensions in H, or why do they want make
But
it same?
one article I have said, I learned that if I choose this normal distribution, it minimizes the overall loss. So that's why they use this normal distribution.
So my question is, why KL divergence is basically loss.
Yeah.
So why using normal distribution reduces the loss? I just can't understand why.
I'm also not sure about how this standard deviation actually minimizes the loss.
Okay, then Shadek, would you please write down
Okay.
this question
Okay.
in some note, and after this seminar, please let me know using the Slack. So make a general announcement about why we use the distribution of age.
Okay.
Follow the normal distribution. Okay.
Okay. So these are the two components. One is the KL divergence, which is to make the age distribution same as the normal distribution, and another is to match the input image. I mean, the second loss, which is the matching the input image to the output image, is done by log probability. That means there is a this is not KL divergence. That means in terms of our image, like for each image will have a pixel of 0 or 1. Output will also have a pixel of 0, 1. So it will try to match each individual pixel, and we'll find the log log probability between these two distributions, how far they are close to each other. So that is another loss. So
the KL divergence is for ensuring that the whatever output the encoder gives is over a range and not just a single value for an image.
KL divergence is only for the encoding part. It doesn't concern about
Basically, it's a measure of the
It's the distance
difference between two distributions.
Yeah.
So the main target of VAE, like say, if I have different classes of input, like say I have this one hidden space and for 2, another hidden space for 3. So I want all the images to be close to a center. Like say all images has a center of mu is 0 and also the standard deviation of 1. But I also want each individual class to be separate from each other. So that means if I want to go from one class to another, there should be some way, like say difference between the features. That's how make it different from these two classes. So all the classes will be centered around same mean and same distribution, but still I want to make them separable. So as you will see in the training, so initially all the classes should be like say there should be a large gap between two clusters, but if we train more and more, this all classes will come close together, but still there's a separable. So I can now code.
Okay.
So I need libraries which is TensorFlow, NumPy, need the MNIST dataset, which is in the TensorFlow library. Also for visualization, I need matplotlib. So now first try to define the structure of our graph, of our computational graph. So let's see, we'll have part for encoder, make encoder. So I'll define a function as make encoder. So I'll also make another is for decoder. Also I need to provide the input data.
What does the make template function does?
It makes from a function. So it will capture the return value from that function and will save it here. So it's just one portion of the computational graph, which is basically represents a node. Like say in computational graph, each basically it's composed of different nodes. Each node has contain a certain value. So this encoder contains a certain node, and decoder is also represents a node.
So it's a node.
Yeah.
And the string is the name of the node.
Yeah.
Okay.
So our image size is 28 by 28. The first none is basically to represent the how many images we want to provide to our network. So that's why it's a three-dimensional.
I have a question. So this placeholder is also making node, isn't it?
Yeah.
And what's the difference between the placeholder and the make template?
I think like say I will define a function separately, which would be the make encoder and make decoder. So instead of writing function here, I can write it in a separate file and just load it here.
Okay.
So there's the also I also need like say all the statistical distribution which is comes from tf dot so this distribution has all the standard statistical distribution inside, which is Gaussian, Bernoulli, or many different distributions are in there. So now, as I said, I want to make a prior distribution which has a mean of 0 and variance of 1. So for that, I'm defining function. So this mic prior will sample from a mean of 0 and variance of 1. So we want our hidden size to be 2, such that we can ultimately show it in a graph.
The last line.
Is 2 big enough? I mean, because you have to represent all the features, all the images.
So you mean, what do you say?
If you have a hidden state of 2, is that big enough to represent all the features from it?
Yeah, for a handwritten digit, it's big enough to build a cluster and to separate each class. So this likelihood basically means that how much this the input data is similar to the output data. So this is basically a loss that defines it basically means similarity, not loss. And also divergence.
나 붙여놓으면 못 받는다니까. 왜 자꾸 전화해?
Can you make it a little bigger?
문자 메시지 계속 보냈는데. 알았어. 카톡으로 얘기해, 카톡으로. 그러면은 뭘로 연락할 수 있어? 이메일도 안 돼? 그냥 급한 게요?
So a KL divergence is performed between the prior that we are getting from mean of 0 and variance of 1 with the posterior. Posterior is just the output of encoder. So this elbow means basically the mean of difference between likelihood and divergence. That means we want to maximize elbow. That means we want the likelihood to be more and divergence to be less.
What is the elbow means?
So, elbow means the loss function, the loss, which basically
No, why elbow?
L.
Why is the name elbow?
Actually, I think it comes from like say in cluster size, which like say there is a way in to find the proper cluster size. So it finds like say at which point the loss is minimized. So from that thing, and I think the elbow came.
Is it aggregation? Is it aggregation? or-
Application.
Abbreviation. Is it like a short form?
Yeah. I think you can give it any name.
The decoder output, is that going to be a probability distribution?
The decoder output.
Yeah. Because you're calling log probability on it.
Decoder output would be an image. So ultimately, decoder output is the last stage. So ultimately, its output would be an image. So I will define decoder. So minimize. So as we want to maximize elbow, but as our optimizer work for minimization, so it will be minus of elbow. That means our optimizer work for minimization, but we want the maximization of elbow. So that's why I'm defining it as minus.
Elbow is evidence lower bound. Evidence lower bound.
Okay. And we also like say sample from the from our normal distribution, and we will try to see the output. Like say we will do that for the 10 images for 10 objects. Then we'll define the mean. Now we'll work for MNIST data set.
What is 28 by 28?
This is the size of the input. That is the size of MNIST data. And also ultimately I want to visualize the data by plotting.
Sorry, maybe you need to put one closing bracket in samples.
No, it basically ends here.
Oh, it's there. That's it.
Actually, I have to know. We write the two function for encoder and decoder. So initially, I am flattening the image into a single vector, and then it will pass through a dense layer.
So you wrote the same line 2 times.
Yeah, that basically means two layers,
Okay.
two dense hidden layer.
Is the size still 200?
Yeah. X. See, in this log variable is basically for mean, and scale is for the standard deviation. Soft plus is the activation function which is similar to ReLU, but it has a differentiability on input x on 0. So this is a kind of same. So this encoder will generate a vector of size, size of hidden size.
Sorry, what does that soft plus do?
Soft plus is activation function, as like ReLU. Do you know ReLU for?
How does soft plus look like that? What is that?
It's basically ReLU is straight at 0 and like that. So when you are the curve.
That's the soft plus?
So it's differentiable even at that point.
And also we'll make another function for decoder. This is for
I think, can you check the third x fourth line, like x equals, is it what will be the dimension of the x?
the dimension of x would be the, like say your input as a like a code.
The size of code is 2, right?
Yeah, like say it comes for 10 by 2, like 10 by 2. So ultimately here the output would be here 10 by 200.
Mm-hmm.
Also here it will be what? Still 10 by 200. That means I mean output will be 200. Yes. X. Like say in like say I'm passing a data of 10 objects. So here in this stage the output will be 10 times 748. That means this basically flatten the input image, and I'm passing a data shape which is which is 28 by 28. So it basically flattens the input image and makes a dense layer of 784 node.
Okay. Yeah. Okay. I think now I got the idea. So each. Okay, let's go.
Okay. So, but ultimately, as the output of decoder, we want to convert it to an image. So we'll reshape it to our data shape. So, like say for 10 images, it will convert it to 10 times 28 by 28.
Why we the reshape spelling is error? There is a spelling error in reshape.
Or SH.
Yeah. And what is the scale -1?
-1 is basically means it can take any size.
Okay.
It can take any size. And data shape is for 28 by 28.
Mm-hmm.
So ultimately, if I give 10 images, it will be 10 times 28 by 28. For 100 images, it will be 100 times 28 by 28.
So data shape is 28 by 28.
Yeah.
So what happens if we add -1 plus 28 by 28?
So it makes the shape as this one. I mean that's how it works. Is it basically 28 by 28?
Mm-hmm. So what's the result of the -1 plus 28 by 28?
So it will. So it basically means, like say, if you give 2 minus 1, so it will convert it to, like say for 10 images, I mean you cannot give 2 minus 1, 1 is 5, so it will become 2 times 5 times 28 by 28. Does it make sense? Like say you have one dimension of minus 1 comma 5 plus 28 by 28. So 5 is fixed. So ultimately these two dimensions will make 10. So 5 is fixed. So we have just two remains. So minus 1 will be filled by 2. So
Okay, so one dimension you're specifying, and
Yeah.
the other dimension it automatically fills based
Yeah.
on the total number of
Yeah.
dimensions.
based on your batch size or whatever.
So that is 10 basically.
Yeah.
So it flows.
How we can do element-wise sum?
Elementary sum.
Yeah, I have a stupid question. So, yeah, I think I have a stupid question. So, my question is, somehow generates this. What should we do if we do element-wise sum, which is
4
yeah. Any idea?
add to what is it does
No, but actually, what you got first was correct. So it's going to become minus 1, comma 28, comma 28.
Pardon me?
What you did first was correct. So it's not doing element-wise sum. It's going to become minus 1, comma 28, comma 28.
Ah, yeah.
Yeah,
I
he
know
wants to-
-1 syntax. My question is,
how to do element.
yeah, how to do? So this is a numpy array or is it array?
No, this is a normal array. Python array.
Python.
Yeah. Data shape is not a numpy array.
Yeah.
So you can't do an
Okay.
element-wise.
So this is a Python array. So that's
Right.
why they did a concat.
Right.
If it was a numpy
Array
array.
to do.
Okay, fair enough. Now I got it. Thank you.
So now I will apply this independent distribution, which will use for Bernoulli distribution. Like say, for each pixel of the image, we'll have a Bernoulli distribution whether it would be 0 or 1.
Shade? Actually, we have to go. We have to continue on the motion capture
Okay.
at 2:20. So I think we have to end it here. Would you mind continue next week? And
Okay.
can you do the how we? I have two questions. It will be great if you can explain better.
Okay.
So what is the benefit of the generative model?
Okay.
And give me a concrete example, simple example,
Okay.
right? And the second one is how we can define the loss. So
Okay.
why we define the two terms in the loss, likelihood loss and divergence loss.
Okay.
Yeah, likelihood loss makes sense to me. Divergence loss, why divergence loss makes sense, and what does the ELBO, evidence lower bound, means?
Okay.
So you don't just prepare some simple examples for each concept, okay?
Okay.
And let's continue next week.
Okay.
Alright? Thank you, Shadek.